All right, for honor students, this is just a continuation of where we left off yesterday when we talked about spontaneous reactions. We're just going to look a little bit closer specifically at Gibbs free energy and the various conditions and combinations of enthalpy and entropy that can occur that can help us determine if a reaction is spontaneous or not. So as we talked about yesterday, delta G is called Gibbs free energy exchange. This takes into account both enthalpy and entropy, and also temperature and its role in spontaneous reactions. And basically allows us to indicate whether or not a reaction will be spontaneous. Remember, spontaneous means it's going to happen on its own without us forcing any conditions upon it. So delta G is our free energy. Delta H is our change in enthalpy or energy. We have our change in entropy, and then we also have our temperature in Kelvin. So again, temperature is a factor and can influence whether or not a reaction will be spontaneous or if it will not occur at all. So when delta G is negative, this means the reaction will be spontaneous in those conditions, specifically temperature conditions. So for an example, this reaction is endothermic with an increase in entropy. And I'm getting endothermic off of table I in your reference tables. And then the increase in entropy is coming from the fact that we're going from a solid to aqueous solutions, which have much more energy than our solid. So that means that our delta H is positive and our delta S is also positive. We have an increase in entropy that's favorable, but endothermic is unfavorable with this positive delta H. So what that means is that this is not spontaneous at room temperature, but will occur if we heat it. And why that is going to occur is if I heat it, I'm going to be increasing the T delta S part. So by heating it, we can see that if I increase or if I decrease temperature, okay, so I make this part of my equation smaller, it allows delta H to be greater. So we have a large number minus a small number, which means that delta G is going to stay positive and be non-spontaneous. However, that non-spontaneous reaction at a high temperature, by increasing temperature here, we would have a small number minus a large number, which means that we end up with a negative delta G. So I can cause, at a higher temperature, this reaction to be spontaneous. On the previous slide. A couple things just to note, that reference table back in concept W notes actually lists the free energies of formations, but also the energies that gives free energy. And we'll take a look at that. If it's negative, that means that it's going to form spontaneously, and then if it's positive, only the decomposition of that compound is spontaneous. So keep that in mind. If your delta G is positive, the decomposition of the compound will be spontaneous. So here was when we looked back at the heated formations. Now we're looking at the free energy of formation with our delta G. And again, the negative ones are going to be spontaneous in their formation, while the positive ones will only be spontaneous under these conditions for the decomposition of those reactions. All right, so here we're actually going to calculate the entropy or the change in entropy for the formation of 1 mole of copper sulfate under our standard conditions of 1 atm and 298 Kelvin. So here's my formula. I'm going to, and sorry, there's a double minus there should only be 1. Our delta G is going to come right here from the negative 708.7. Our change in enthalpy, our delta H, we're going to take from our heat of formation, which is our negative 770.8, so I'm taking that number off of there. Our temperature is 298 K, and then I'm going to be searching for delta S. So here I can see then that by plugging in those values and solving it by subtracting or adding, we get that our delta S is negative 0.208 kilojoules per Kelvin. Usually we express this in joules per Kelvin just because it tends to be an incredibly small number, but we do see that we end up with a negative delta S, which is just something to keep in mind, that we had a negative delta H and negative delta S, and how we had to have a specific temperature in order to get this negative delta G. All right, so just a little review in summary that if we have negative delta H and a positive change in entropy, it's always going to end up with a negative delta G, so it's always spontaneous. These are both favorable conditions. However, if delta H is positive and delta S is negative, which are both unfavorable, it's going to be a positive delta G at any temperature, so it's never spontaneous. We can see that delta H and delta S are both positive. It can only become a negative delta G, so it can only be spontaneous at high temperatures. If both are negative, we can only get delta G to also be negative if it's at low temperatures. So in order to make it negative and make it be spontaneous, we have to have that reaction occur at a low temperature. So I know that was like a kind of a little bit pieces of information. We're going to be applying it. The big idea here is that you're able to manipulate that formula using the formula and the given values in the table earlier in your notes to calculate your entropy, but also using values given to you to calculate delta G to see if you have a spontaneous reaction or not. And then also understanding how delta G is influenced specifically by temperatures when you have an unfavorable condition with either enthalpy or entropy. So again, you're going to be applying this a little bit more in class to hopefully clarify some of it, but at least have it down in your notes so you have it as a reference, and then you can go ahead and write a summary or go and complete your Edmodo quiz.